Hey, thanks everybody for watching this video. I'm Binghui Peng from Columbia University. It's my great pleasure to present our work on fast spectrograph minimization and applications to correlated equilibrium in this video. This is based on joint work with Avi Rubinstein, and the work is going to appear on STOC 2024. In the field of game theory, people study multi-agent system where agents could refer to machines, robotics, humans, where they all need to interact with others in such multi-agent system. If you think about a system that involves multiple intellectual agents, the first challenge actually comes from conceptually. And if you want to make any prediction or you want to solve the system, you realize that most likely it's impossible to simultaneously maximize the objective for each agent. Because this agent could have different opinions, different actions, and because they have different objective or reward functions. And so this means most likely it's just impossible to make everybody the most happiest one. So instead of trying to simultaneously maximize the objective of each agent, people trying to search for an equilibrium. Equilibrium is an important concept from the community of game theory. And from high level, equilibrium refers to a state of the game such as no agent has incentive to deviate. For my opinion, I think equilibrium is more like the minimum requirement for the solution or predicted outcome of our multi-agent system. Because if your predicted outcome is not equilibrium, then it means the solution is not stable because some agents are not happy with its current status and they try to escape from its current state. And it's not because it's not stable, it cannot be the final outcome of our system. More concretely, there are two famous solution concepts of equilibrium. The first one, probably the most famous one, is called the Nash equilibrium, which is proposed by the famous mathematician John Nash in the 1950s. Nash's theorem points out in that in every game, there are choices, independent choices for players, such that no players want to change. Or in other words, given other players' choices, the player does the best they can do in the equilibrium. There's an alternative notion called correlated equilibrium, which is proposed by the Nobel Prize winner Robert Altman in 1974. Correlated equilibrium is a generalization of Nash equilibrium because it allows correlation between player strategy. More formally, Altman's theorem points out in every game there are correlated choices for players, just as no players want to deviate given other players' strategy and public signal. The field of algorithmic game theory further takes computation into consideration, and in terms of equilibrium computation, there are two fundamental results. The first law of work points out that Nash equilibrium is actually intractable from a computation perspective. People prove it's pretty hard to find a Nash equilibrium even for two-player normal form games. The conceptual message here is that Nash theorem is very beautiful and Nash equilibrium is very natural that will exist. But unfortunately, in complicated systems, just hard to find. And even the most powerful computer and the smartest algorithms cannot hope to find it. So it's always there, but cannot hope to find it. On the other hand, people have found that the correlated equilibrium actually allows polynomial time solution because it can be written as a solution of a linear programming. And more amazingly, people have shown that actually correlated equilibrium can be the natural outcome of decentralized learning. Let me explain the connection between decentralized learning and equilibrium in more details, and which is actually the focus of this talk. The folklore theorem states that if each agent runs an online learning algorithm that has low swap graph. I will explain the notion swap graph in a few slides later, but now you can imagine if each agent runs some learning algorithm has been the property of being low swap graph, then the empirical distribution converges to a correlated equilibrium. More quantitatively, people have shown that if the learning algorithm has at most epsilon swap graph, then the empirical diffusion converges to an epsilon approximate correlated equilibrium. The more technical part is actually to design no swap graph learning algorithms. A classical work of Avram Blum and Isam Mashas, which appears in the early days of recent game theory, shows that it's possible to obtain epsilon surrogates in n log n over epsilon squares iterations. And therefore, by plugging in the above Fock-Law theorem, people have shown that they can find an epsilon approximate correlated equilibrium in n log n over epsilon square iterations of decentralized learning. Here, n is the number of action for each player. The open question asked by the author, Alvin Blum, and myself is, of course, can you minimize swap graph faster? And if so, by plugging the connection between learning games, you can immediately get a faster decentralized learning algorithms for finding a correlated equilibrium. Our main result in this paper and also appears in a concurrent work by Duggan, Dasklakis, Golowich, Fisherson, which also appears in STOC24, is that we show it's possible to have exponentially faster algorithm. In particular, we show it's possible to obtain epsilon swap graph in polylog iterations for any arbitrary small constant. So this gets exponential improvement in terms of the number of actions. But on that, and solve the open question of Aaron Blum and the assumptions. You may note that the dependence on epsilon actually gets worse. Our second result shows that the minimums, the min-max, this is kind of best one can hope because the min-max swap graph is the minimum for these two algorithms. Our algorithm has many applications in terms of correlated equilibrium computation, and let me briefly mention its applications, and let me first mention some open questions existed in the field for a long time. The first line of open question concerns the efficiency of finding a correlated equilibrium. There's a quest for finding more efficient algorithms. For example, people care about computation complexity. And one fundamental question is that how fast can one find a correlated equilibrium? The best known algorithm has cubic runtime in order to find an approximate correlated equilibrium. Well, there's no non-trivial lower bound than the linear lower bound. People also care about the communication complexity for correlated equilibrium. And in particular, people care about how much information they need to exchange in order to reach a correlated equilibrium. The best known communication protocol takes roughly linear number of bits. Well, again, there's no non-trivial lower bound than the log n bits lower bound. Similar open question exists for query complexity, encounter dynamics, and so on. The first applications of our faster swap graph learning algorithm is that we solve all these questions and give near optimal algorithms. For example, for computation complexity, we improve the runtime from cubic to linear, and this solves the open question by Papadimitriou and Ralph Gardner. We also improve the communication complexity from linear to polylogarithmic and solve the question by Babchenko and Rubinstein. Similarly, we improve the query complexity from quadratic to linear, which is optimal. The second line of open question exists in the literature is about the curse of dimension for actions. In particular, there are many scenarios, many applications in game theory, such as the strategy or action space could actually be exponentially large with respect to the input parameters. For example, this includes a Bayesian game, extensive game. If you have not heard of this term, I just want to note that poker and auctions belong to Bayesian or extensive game. The action space is exponentially large because for these games, the action space is a mapping from the private information of the game tree to available choices. So exponentially large with respect to the game size. Because of this, even a linear dependence on the number of action is not enough. So we cannot directly use Blum and Masel's algorithm because a linear dependence on action space means sequentially large dependence on the game size. Also, you cannot hope to solve it by linear programming because it involves sequentially large number of variables as well as number of constraints. Because of this, people have conjectured that correlated equilibrium, in particular normal form correlated equilibrium, It's computational intractable, and there is one major open question in this field. Using our algorithms, we actually refute this conjecture, and we give the first polynomial time algorithms for Bayesian and extensive form games. Now, let me finally dive into a little bit more details of our main results, and let me explain the definition of swap regret and what's our no swap regret learning. The swap regret is defined first in the online learning setting, so let me first define it in the online learning setup. Imagine an agent wants to make a repeated decision process for a sequence of tiered rounds. It can choose from a set of n actions empirical at each round. The agent picks a distribution over a set of n actions. Then the nature reviews the reward of each action. This is repeated for t rounds, and the swap regret is defined as the maximum gain one could obtain when using a swap function over one's case stretch. More mathematically, it defines the difference between two terms. The second term is just the reward of the algorithms. Okay. The first term is the hypothetical reward of the algorithms. If the agent switch its actions in a consistent way, or in other words, it's the hypothetical reward agent would receive if it switches to target action strategies. Okay. And finally, let me explain our algorithms and the intuition behind it. Our algorithm is actually quite simple, and we call it multi-scale multi-weight update. Here, multi-weight update is some classical regret mitigation algorithms for online learning. And for this talk, you do not need to know the details of it. The idea is to maintain multiple threads of algorithms, where each thread of algorithms restart in different frequencies, and in each restart, it just runs multi-weight, but update in different paces. Each thread gives some decisions, and the final algorithm just plays uniformly over these threads. Okay, let me just summarize again. Our algorithm has multiple threads. Each thread just runs multi-weight, but it updates and restarts in different frequencies. The final algorithm just plays uniformly over them. The intuition of this algorithm is that the recursive application of multi-weight, but in different scales, kind of catches the risk. And because the surprising simple algorithm could give the optimal regret guarantee for swap regret and solve all these questions on correlated equilibria. Let me finally summarize the major part of our work in this video. In summary, we give a simple, faster, no swap regret learning algorithms. It has many applications to correlated equilibrium computation. In particular, it gives the near optimal communication, and query complexity for finding approximate correlated equilibrium in normal form game. And it gives the first polynomial time algorithms for games with potentially large action space, including Bayesian game and extensive form game. Thank you for watching this video.